Check in, can you hear me?
Yes, very well. Yes.
Thank you, Salvador.
Yeah.
Thank you. Okay, we're going to restart our meeting. This is the afternoon session. We're going to start with Stella Garces, who is going to give a review in dark matter searches and mainly in neutrino physics. Stella, can you please share your screen?
Okay, I'm sharing my screen now. Only the keynote.
Okay.
It's there.
Yeah, we can see that. If you can probably close the slide layout
Highlight. Okay.
just to have your slides larger. Yeah, and maybe the one at the right.
Yeah, I don't know how to do that.
Just click on format maybe, and that will close. No, at the top right, just click on this icon that has a brush. This format there we go.
But can you see the full screen, or is it?
It seems fine to me.
Yeah, I think so.
So please go ahead, Stella.
Okay, well, thank you to the organizers for the invitation. And as you can see from the original title of my talk, it was advertised as direct detection dark matter searches, but because we are limited in time and also to set the stage for this session, I think the following talks will be more related to neutrino physics. So I will be focusing on neutrino physics and also I will make a few comments on dark matter and especially on direct detection experiments. Well, the news have been overwhelming the last couple of weeks and maybe months. So some of us have altogether stopped watching the news, but I would like to collect the last news. Well, not that have not always been bad news, because it's always nice to see beautiful sunsets and beautiful neutrino and dark matter detectors displayed in the press, for example, in the New York Times. And that's why I wanted, and also because in this year, not only terrible things have happened, but also very exciting science results have been released. So, and some of them happened in the past few weeks, where we had this amazing Neutrino 2020 conference that was also like this one, like this meeting held in online, fully online. And this is unprecedented, but there are also some very good news that are unprecedented that I would like to share with you to cheer us up. So I wanted to focus my talk mostly on these news. Of course, this will be, I must disclaim that this will be my incomplete and biased view of the last events, but I hope you enjoy it as much as I did. Well, regarding neutrino physics, this is the outline of my talk. I will present what we know so far about neutrino physics, this 3 neutrino oscillation picture. But however, we have some experimental and theoretical anomalies that all point to the possibility of the existence of a 4th sterile neutrino. So I will say a few things about that also, and about this new recently discovered process that was proposed almost 40 years ago by Friedman, where neutrinos can interact with the nucleus. And this is done coherently via the neutral charge. So I will mention the progress so far that we have on coherent elastic neutrino nucleus scattering. And I will mention a few of our phenomenological works on that. And also what's the perspective for the experimental part on reactor neutrinos and the recent measurements on spallation neutron source neutrinos. And I will finish my presentation mentioning about the direct detection dark matter experiments that have recently, well, especially in the xenon result for electron recoil data. And I will try to summarize what the future of dark matter experiments have for neutrinos, where they can also be a signal. Well, today, or so far, we know about neutrinos that they interact, so therefore they must have mass, but it's not yet solved what's the mechanism where they acquire mass. And that's why we don't have a full theory of how is the flavor. And also we don't know about the nature of neutrinos. We don't know if they are Dirac or Majorana, and there are many proposals in the theory part, but there are also experimental searches on the probable neutrinoless double beta decay that could be a sign that they are Majorana neutrinos. And so far, I will try to summarize that we in the present are making more specific questions about neutrinos. 20 or 30 years ago, we wanted to know if they oscillated after they were, and the solar neutrino problem was trying to be solved. But now we know a little bit more, and we can make more specific questions about what are the mixing angles and what are the mass splittings, what is the mass hierarchy. And also we can probe if there are sterile neutrinos, also the mass ordering and the possibility to have a CP violation in the lepton sector. So this is the 3 neutrino oscillation scheme that has been parameterized in this way. This is a practical convention where atmospheric reactor and solar neutrinos have sensibility to different phases and different mass splittings. Also, we don't know if the hierarchy is normal or inverted. And we have 3 flavor states that mixed in the mass states. And from different experiments, this is what we know. So far, most of the parameters have been measured, and we know them with around 10% certainty, or that's the level of the uncertainties that we have. This is just a compilation of one of the groups that makes the global fit. This is also one of the nice news I wanted to share with you, because this is very recent, as you can see, and it is compatible with all the global fits that are done. And in this slide, I want to summarize what we know so far about neutrino oscillations in the known 3 neutrino mixing scheme. We know the masses, the splittings, and all the mixing angles have been measured so far. And we know that there is still to know the delta CP angle, the phase that will explain delta CP violation that's necessary to explain and comply with the Sakharov conditions. And we are now, after 20 or maybe 30 years of from where we wanted just to know if there were oscillations, and those were measured from the sun and from atmospheric angles, from atmospheric neutrinos. That was before done only, or the experimental capabilities were to do it in a 2 neutrino flavor scheme, but now we know that the reactor angle θ13, it's non-zero, but it's very small, and the subleading contributions in oscillations to this parameter can be taken and must be taken into account. But there are experimental proposals for the near future that are very exciting and will help to know these oscillation parameters with more and increasing precision at the 1% order. And this great achievement in the future, this has been achieved by increasing detector size, by having better sensitivity, and also in the theoretical part, there has been a great progress, many theoretical possibilities, and also very analysis tools and very simulation tools. Also, we moved from analyzing 20 years ago only natural source neutrinos from the sun and from atmospheric to now using the man-made neutrinos from accelerators and reactors. And also we have a possibility to measure even higher energies, and it's remarkable that these high energy atmospheric neutrinos can be measured in IceCube and actually can be used to get oscillation parameter fits. So this is a very nice plot that summarizes the capabilities, the experimental capabilities from different targets, and in order to analyze different mass splitting ranges. And in blank are the experiments that are future, that are going to be constructed. Also, one of the nice news of 2020 is the approval to build the Hyper Kamiokande. And also there have been very nice results from Proto-Dune that are moving to the construction of Dune in the near future. This lies in the delta M32, the atmospheric mass splitting, that will be measured with increased accuracy, and maybe we will finally know its sign, and this will disentangle the two possible neutrino hierarchies. Also, in the case of the possibility of sterile neutrinos, there are many experiments like Prospect, Stereo, and Juno. Juno is from reactor neutrinos, and others from accelerator neutrinos that are going to help to finally solve this anomaly. And speaking of sterile neutrinos, there are 4 sources of 4 hints that at almost 3 sigma, at a 3 sigma level, can point towards the possibility of the existence of a sterile neutrino. And this sterile neutrino is very strange because it's a very light neutrino that needs a mass splitting of the order of 1 electron volt. And these 4 different anomalies can be splitted in this way because for the reactor antineutrino anomaly, where a 6% mismatch in between the theory prediction and data was observed. And also in the gallium anomaly, where less than the expected L neutrinos from a radioactive source were observed. These two can be, or some authors propose that could be due to purely theoretical uncertainties that are at the order of 5%. And in the case of the LSND and mini-boon, it's for accelerator neutrinos from mu neutrinos. The mini-boon actually was built to check the LSND anomaly, and it is done at higher energy neutrinos and higher baseline, but the ratio L/E, it remains equal, so the same mixing angle can be studied. And so far, one of the latest news from mini-boon, it's that the anomaly remains. They have an excess of over the expected electron neutrinos, and they will soon release data. This is the last results from mini-boon, and these were also published in the last days. So from this appearance probability plot, one can see that both LSND and mini-boon follow approximately well this probability appearance line at 1 sigma. And these are the delta m squared values that are for LSND close to 1 MeV electron volt squared, and around in that order. And moving to the case of the neutrinos from the sun, we have learned a lot from the sun thanks to neutrinos in the last decades. And as John Bacall said, he said, if I had not lived through the solar neutrino saga, I would not have believed it was possible. And maybe he wouldn't believe now the newest results and all the amazing results from the Borexino collaboration. They, over the past few years, they actually measured individual contributions to the neutrino solar spectrum. They measured the PEP and the beryllium-7 contribution, and also the monoenergetic line from the PEP neutrinos. And from the latest news from Borexino, they also claim to have observed the CNO cycle neutrinos that are a subleading contribution. It is said that 99% of the energy of the sun is released in the form of neutrinos, and there are two main cycles by which Borexino, by which the sun, it's converting helium into hydrogen into helium and then into heavier nuclei. And this amazing result they achieved by perfectly or very, very, very good identifying the bismuth-210 and lead-210 backgrounds from beta and alpha decays. And in this color plot, they show how over time by controlling temperature, they were able to identify and reduce these backgrounds. They finally measure 7.2 CNO neutrinos per 100 ton, including statistical and systematical errors. And in the Earth, this corresponds to a 7 to the 8 per centimeter squared per second neutrinos. So this is the final results from solar neutrinos, and something that seemed in the past decades very, very hard to do. It was a shift. It's also published in the archive by this number. And now I will move to the coherent elastic neutrino nucleus scattering that was proposed almost 40 years ago by Daniel Friedman from Fermilab. And something that I like to remember and comment on is that the experimental proposal for this process, the neutrino coherent elastic neutrino nucleus scattering, actually preceded the experimental proposal for dark matter searches. And it can be seen here from this paper in the left. It's the original proposal on the weak neutral current. And this process, it's a standard model prediction. And also it's always reference this Drucker and Stodolsky work, where they propose the experimental detection first ever from this work. And in 1985, the first experimental proposal for searches of dark matter candidates, actually it references the work on Drucker and Stodolsky. So I find this very amazing. How, well, SEVENS is a neutral current standard model interaction that it's clearly predicted, and it has experimental difficulties, and because it gives a small nuclear recoil and very small energies are very difficult to measure, and for this we need very high neutrino fluxes, but also very low backgrounds and very well identified backgrounds. And this condition happens for solar reactor and some other sources of neutrinos. The neutrino coherent neutrino elastic neutrino nucleus scattering cross-section has this form, and it is proportional to the nuclei mass, but also the maximal recoil energy that the nucleus can have, it's inversely proportional to the nucleus mass. So this tells us about the experimental complications in order to measure very small, of the order of few keV nuclear recoils. So that's what also dark matter searches are looking for, very small nuclear recoils. And this is the cross section for where the FB, it's the nuclear form factor that becomes important for neutrinos from spallation neutron sources. And it's almost equal to 1 for reactor neutrinos. And from this form of the cross section, looking at it's also, we can see that it is sensitive to the weak charge. So standard model tests can be done, and it is proportional to n squared, and it's the number of protons in the nucleus. This cross section is enhanced by n squared, so it is actually bigger than neutrino electron scattering, and orders of magnitude also bigger than inverse beta decay. It's the golden channel where the first neutrinos were detected, and it's the one we use for reactor neutrinos nowadays. And also has this advantage that unlike the inverse beta decay, it is thresholdless. So many applications can be done. There are many interesting possibilities to study using this process. Some of them are reactor monitoring, nuclear form factor studies, electroweak precision tests. Supernova neutrinos could be detected if are in the Magellanic Cloud proximity. And also it is a background for dark matter detectors. And many beyond standard model interactions can be probed, for example, in specific models or in the non-standard interactions scheme. Many electromagnetic properties of neutrinos can be studied using this process, like the neutrino radio, electroradio, or neutrino magnetic moment, and also at the right baselines, studies in order to probe sterile neutrinos can be done. And the case of non-standard neutrino interactions, I am sure Dr. Newton-Natt will tell us more about it, and also Luis Flores in this session in the next talks. But this neutrino interaction, non-standard neutrino interactions imply a modification to the vector and axial couplings to nucleus in this case, but it can also affect not only detection, but also the propagation in neutrino oscillations. In the case of coherent neutrino nucleus scattering, they modify the vector and axial couplings. So beyond standard interactions can be probed in this process. Well, this not so recent news, but also very impressive news from 2017 was the first time this process was ever detected, and also in the cesium iodide detector. But it actually made the breakthrough of the year of the Science magazine, and it made to the cover. And what is most impressive of this detector, as you remember, the cross-section is orders of magnitude bigger than the usual detection processes cross-sections. So this implies a reduction in orders of magnitude of the size of the detectors. And this is the smallest detector to ever detect neutrinos. This is a pint size, 14 kilogram, that can be handheld. And this was achieved in the Oak Ridge laboratory by the Coherent collaboration. They have a complete program with using the different technologies and different targets. And also news from the Coherent collaboration was that this year they finally measured also using liquid argon as a target. And you can see from this plot, this follows the n-squared behavior for the cross-section. This is here in this blue square for argon and the 2017 measurement in cesium. And this already gives very useful and important information about the nuclear structure, because we can measure with increased precision the form factors and test different quenching factor and form factor models. And actually, another of the good news that I wanted to share with you, it's that just last week on June 22nd, the Coherent collaboration made this data release. And data I didn't mention here, but it is how the first detection of coherent neutrino nucleus scattering on germanium, on the cesium iodide detector, made this exclusion for neutrino quark interactions beyond standard model interactions in the NSI scheme compared to previous charm neutrino electron scattering, neutrino quark scattering, sorry. And now using different targets and different nuclei as target can be complementary and can be useful to disentangle the possibilities of NSI. This is shown here in this work and this result from Coherent. But this was measured using spallation neutron source neutrinos or pion decay at rest. But there are many experimental searches using different technologies in order to detect for the first time the coherent elastic neutrino nucleus scattering from reactor neutrinos. And for this are already being deployed different detectors using, for example, Texono and NuGen use, as well as minor germanium as a target. The CONUS experiment uses germanium as well. And the RED experiment in Russia uses a xenon, liquid xenon single phase detector. And in the South Pole, we have only CONI. It's a CCD's experiment using silicon as a target. And also I will mention that no significant, well, neutrinos from reactors have not been observed yet in this process, but CONI already made a nice exclusion to new physics. And another experiment that I want to mention is the SBC, is the scintillating bubble chamber. This is a collaboration from Mexico, Canada, and the USA. And I will mention later more about this one. And well, the possibilities to sevens are enormous, and there is very rich phenomenology that can be studied. And for example, in the case of the standard model tests, for the weak mixing angle, we know this parameter has been measured with very high precision at the C-pole mass. However, in neutrino processes at very low energies, for example, using neutrino electron scattering, we, in this previous work from 2016, we showed that there was very much room for improvement, and this can be achieved, as we showed in 2018, in future coherent measurements in reactor neutrinos. This is the projected sensitivities for Miner, Retzian, and CONI, and they use different targets also. And also non-standard interactions can be studied, and actually there can be interplays between nuclear parameters like the neutron radius and with NSI. This one on the left is using the cesium iodide data from coherent and combining with an expected result from reactor experiment CONUS, and for a specific set of quenching factor and form factors. And this in the left, it's how combining the different targets, in this case silicon and germanium, can very much reduce the increase the sensitivity and already exclude some new physics scenarios. Also, the case of sterile neutrinos can be studied using this reaction, and in this work we did for projected sensitivities using xenon and germanium as a target, and it put in the same footage as the reactor antineutrino anomaly. It could already exclude the best fit point of the reactor antineutrino anomaly. And also, I think in this session, we will have a talk about sterile neutrinos using sevens, so don't miss it. It's from Oscar Sanders in this session. And as I mentioned before, talking about the great news of this year, the result, well, the standard model structure can be producing neutrinos, but also the existence of other extra vector or scalar mediators. In the case of a vector mediator, we can explore a part of the parameter space of the set prime that cannot be achieved in, well, that could be complementary to very high energy LHC exclusions, for example. And here we can probe a vector coupling, and in the parameter space of the vector coupling, and it's the mass of the mediator. The light vector mediator can be excluded. And here the coherent collaboration for the first time using reactor data from an experiment made this exclusion. And you can check that in this reference. And going back to the scintillating bubble chamber, this experiment proposes the combination of two very successful technologies, not only the pressurized liquid, it's a bubble chamber, but it's also scintillating and combines the low threshold bubble creation with the energy identification of scintillation. And the Physics Institute is participating in this project. And as a predecessor of this project, there is also this proposal. It's not related to sevens. It's expecting to use the inverse beta decay. The PI for this project is Eric Vasquez from IFUNAM, and there is already an agreement to use the ININ Triga reactor as a neutrino source. We estimate that in 3 months of data taking, a positive signal could be done. This will have an acrylic vessel filled with 100 kilograms of scintillator doped with gadolinium, and it will be surrounded by silicon PNs. And this can be upgraded to 5 modules to have up to 500 kilograms. And here one can, and this is a very exciting project that I wanted to talk about, and will be a predecessor for the SBC. If it's successful, maybe the SBC will come to a Mexican reactor.
5 minutes left.
Thank you. So, well, in these 5 minutes, I will try to discuss the recent, the exciting results from xenon 1 ton. But, well, what direct detection dark matter experiments can measure and are looking for, it's the electronic recoils from a chi, from a dark matter particle, and also the nuclear recoil from a dark matter particle. And for this, we need a very low threshold experiments. We need low background environments. That's why most of these are underground. And we need to identify very well these possible sources of backgrounds of gamma and alpha backgrounds from natural decays of thorium and other elements that are naturally abundant. And this plot just summarizes the dark matter nucleon spin independent cross sections and in the solid lines are actual exclusions. So we can see here in xenon 1 ton from the, compared here in the hatch, it's the neutrino floor. And at these low energies where it's almost touching the xenon 1 ton exclusion, the main contribution comes from solar neutrinos, and also the future dark side, Darwin and argon, and dark side and Argo experiments are going to be very, very low, very sensitive to even lower cross sections, and maybe could be where the neutrino floor will be an important background. Well, summarizing here, the also very recent data from xenon 1 ton. Xenon is a dual phase TPC. It's filled with liquid and gas xenon, and from here, and it's surrounded by 2 sets of photomultipliers. It has a drift signal and another one, and it has achieved this very, very impressive result. And this new conundrum in the physics community, where they have an excess at very low energies. And this excess was studied in different possibilities. One of the less exciting is that the xenon experiment is contaminated with tritium decays, or that has more hydrogen than it was expected. Other possibility is the solar axion possibility, that it's also not excluded at 2 sigma. The other possibility is that they are seeing neutrinos from the sun, and these neutrinos have a larger magnetic moment that was ever observed. And making this hypothesis, actually, it could be the possibility that for the first time, the value of the neutrino magnetic moment is bounded from both sides and not just an upper limit. And the other possibility they explored was the case of solar axions and a tritium background. And also this axion proposal is in discrepancy with astrophysical constraints from stellar cooling. And the conclusion from xenon 1 ton is that there is no conclusion, and they will need to see more data from the now under commissioning upgrade of the detector, that it's the xenon n ton. This one will have 3 times the active volume. And so far, the other possibilities remain as anomalies that are favored, are not favored nor disfavored, in 2 to 3 sigma. So this will be very exciting to see what the next months will give for these future results of xenon and ton. And so far, maybe you have seen in the archive many theoretical proposals and many models that can be tested using this data. Some of them are, well, this is very exciting to see an excess of low background. It's very exciting for the dark matter searchers community, because for low background, it's very interesting to see what's the source of this background. And this could be also explained by neutrino non-standard interactions. It's very exciting. And this could be also explained by vector or scalar mediators, and for neutrino self interactions from mirror dark matter, just to name a few, and many, many other more. So this is now a 2 sigma anomaly that could be on the way to consolidate to something more, or could disappear, we don't know. As historically we have learned from anomalies. And but I would like to also mention that neutrino and that dark matter experiments, and also especially the future dark matter experiments, have a neutrino physics potential, because they will be sensitive to neutrino electron scattering. So studies of solar neutrinos can be done there. And also they are sensitive to the coherent, well, they are reaching this neutrino floor where the coherent elastic neutrino nucleus scattering is important. And in these huge volumes of xenon, some of the xenon 136 is also present. So neutrino-less double beta decay searches can be done. And also neutrino searches from sterile neutrinos can be searched in the tail of the beta decay spectrum. And especially in the future where neutrino directionality will be necessary, detection, this would provide the possibility to observe geoneutrinos in dark matter experiments. And also we have known more, and cross sections have been measured with increased precision, and all we can know about neutrinos will be useful for dark matter experiments. For example, the expected the neutrino floor, or the projected limits from Darwin and Argo, could be different for different fluxes and different cross-section measurements that I think Coherent will provide very much better information in argon neutrino interactions. So this is one example of the Darwin proposal that could also see neutrinos from the sun. And this can be compared with Boric-Zeno data in this probability plot for the large mixing angle solution. And just to summarize and finish this talk, I would like to say that the future of accelerator and reactor long baseline neutrino experiments will be able to solve the three neutrino paradigm, and maybe we will have more information about the delta CP leptonic violation. And we are starting to better understand neutrino physics in the increasing reactor and other accelerator neutrinos. Now that we use man-made neutrinos. And also, I think I presented a few of the highlights of the seventh phenomenological and physics potential for reactor detectors at using this kind of interaction. And who knows, well, for dark matter detectors, neutrinos are becoming very important now, and maybe today's background will be tomorrow's signal.
Thank you very much, Stella. So for this nice talk, let's go directly to questions and have a discussion in this talk. Raise your hand. Yeah, go ahead.
Yes. No, I don't. Checking YouTube. There is no questions up to now. And no question in the chat. And up to now, no people raising their hands.
Okay.
Oh yes, we have a question from Pablo.
Pablo, go ahead, Pablo, please.
Pablo, go ahead.
Okay. So can you show again the common explanation of the mini boom and LSND anomalies? Maybe I didn't see correctly. I think that the mass splitting was indicated as well as the mixing angle, and one mixing angle was quite large, right? Or maybe I didn't see it correctly. Can you just clarify that?
Yeah. I think this is the only map.
Yes, yeah, exactly. The plot on the right.
Yeah, the black dot, this black dot is the mini boom result. Mm-hmm. And in here, there are some mass splittings shown, but I think are the best fit points that were used to project this onto the appearance probability line.
So there are a couple of pairs of numbers. One is the mass splitting, but the other one is the mixing angle, right? When you read mini boom best fit, this 0.807.
Yeah, the 0.807, it's the mixing angle. And here it's if okay. The mixing angle is 0.01.
Yeah, that was my question. Isn't this 0.8 sound quite large?
Yeah, I think it's the past best fit point value here.
Uh-huh.
Can you see my pointer?
Yes.
Right here. I think it's the comparison with, it's the mini boom value. No, it's the LSND value.
Okay. Thank you.
That one is the LSND value.
Yeah, thank you.
Okay, are there more questions? Eduardo, please go ahead.
Yeah, maybe you can comment something else about Trino. What is the timeline? Are you already taking data, or what is the plan?
After the Trino, yeah. We are characterizing. I think most of the components have been purchased, and there is disagreement with people from ININ. So we are studying the backgrounds, and we have already studied the flux and compared it to Laguna Verde. That was our first choice, but it was a little farther away from here. Of course, we prefer to go to Veracruz, but I think it's more complicated to get in there for the experiment, to go inside the place.
But when are you planning to install the detector there?
Well, it was a timeline of construction for 3 months, but it's being delayed because we are closed. So I wouldn't say, I would say it's a timeline of maybe 8 months once it's all started.
Okay, thank you.
Yeah, but we don't know when we'll be back. That's the problem. But these silicon PMs have been purchased. The acrylic vessel has been quoted from the company, and the scintillator, the LAB scintillator, is sitting in the lab, and it's kind of dangerous because it's a barrel there. It's 80 degrees ignition point, so we hope that everything goes fine for that.
All right, thank you very much to Stella. We must go ahead and we must move on. So thanks again, Stella.
Thank you.
So now we have the talk by Newton Nass. Please, Newton, could you share?
Can you hear me?
Yeah, we can hear you. So,
you can hear me? Okay.
Yeah, we can hear you. Can you hear us?
Yeah.
All
yes,
right.
Yeah.
So your talk on research development in non-standard interactions, please. Go ahead.
Yeah, thanks. First of all, I'd like to thank the organizer for giving me this opportunity to talk here. So as you can see, I'll be talking about some development in the neutrino sector, mainly focusing on non-standard neutrino interactions. And before I start, I'd like to apologize that currently in the literature, there vast material exists on non-standard neutrino interaction. However, I will be choosing some handful amount of materials, mainly focusing on some of my works. So let's start. So let's start with the standard neutrino interactions in matter. The standard neutrino interaction is matter is that in the electron kind of neutrino interact with the earth kind of matter with the charge current interaction. On the other hand, electron, muon, and tau, all three flavors can also interact with the matter with the neutral current kind of interactions. And how this interaction how changes your vacuum Hamiltonian, which govern your neutrino oscillations, is the one can write down for this interaction Schrödinger type of equations where the HF is the Hamiltonian, and because of these matter interactions, that Hamiltonian HF get modified by this potential term A here, and this is kind of usual your vacuum term. So this A is something one can define in this matrix form, and where it is related to this VCC, charge current potentials, and this is depends on your electron number density. So this is our standard neutrino matter interactions. However, almost 40 years back, Wolfenstein proposed that neutrino may also interact. The four fermions can interact with the dimension 6 operator, and this may affect your neutrino propagation, and which eventually impact on the measurement of neutrino oscillation parameters. So this is our kind of standard neutrino matter interaction, as I showed it in the previous slide, where your standard model gauge bosons exchange. On the other hand, if you go to beyond standard model, where some exotic particle may take place exchange in between while neutrinos are interacting through matter. So these new the interaction is something called non-standard neutrino interaction, and it is governed by mainly this epsilon alpha beta. And this epsilon alpha beta matrix something look like this in the 3x3 form. Now, obviously this changes your Hamiltonian, and along with your vacuum and meta terms as defined earlier, these new terms also appear in the Lagrangian. Okay, so you can sorry, Hamiltonian. So you can see that this is a new Hamiltonian, and now you have to diagonalize it with a unitary matrix to get your correct masses as well as mixing angles. So you can understand that this epsilon is going to impact your masses and mixing angles in the determinations. So we have a model independent bounds of these NSI parameters. So you can see there are 6 parameters. 3 of them are real and 3 are complex. So we have a bound, model independent bound coming from these experiments. For a recent detailed status, you can see this report here. So now let's discuss in the 3 flavor. We know that 3 flavor neutrino oscillations is governed by 6 oscillation parameters. We have 3 mixing angle, 2mass square differences, and CP phases. And among these, we have very good understanding of all those parameters, but with some disagreement. What we do not know in these 3 flavors is that the neutrino mass hierarchy. That what I mean is that we have 3 neutrino, M1, M2, and M3 are the masses. M3 is greater than M1, which is called normal hierarchy, or M1 is greater than M3, which is called inverted hierarchy. This is what we do not know. On the other hand, we do not know also the octant. This plot is little old, but for our purpose, you just focus on that. This theta 2 3 less than 0.5 is called lower octant, and theta 2 3 greater than 0.5 is called higher octant. So this is an ambiguity also we do not know. On the other hand, delta is not equal to 0 or plus 180 is implies CP violations. And these will, though with the current global field data as well as neutrino oscillation experiments, we have a hint towards CP violations. Is it maximal or not? It is a question which till there is an ambiguity, but it seems there will be a CP violation like quark sector in the lepton sector too. So these are the unknowns in the neutrino oscillation sector in 3 flavor parameterization. However, as I discussed previous, if nature also support non-standard neutrino interactions, then this is going to impact all those measurements. So out of these 3 cases, my main focus is on neutrino mass hierarchy. I will be going to talk about in this talk on neutrino mass hierarchy. So for the determination of neutrino mass hierarchy, the DUNE, which is a deep underground neutrino experiments, is a proposed future experiments at the Fermi lab, which is a large source to detector distance, and hence it has a more matter effect. And it has been studied that DUNE will be able to resolve this hierarchy sensitivity. You can see from this cartoon that almost 5 sigma for any values of delta Cp if there is no new physics in the standard 3 flavor formalism. However, there are many studies if there is a new physics, something like that I discussed, non-standard neutrino interaction, then this determination of neutrino mass hierarchy can be affected by the NSI. And in that respect, there are many studies has been done. One of the study what I am going to discuss, which we have looked a few times back, is that something called general mass hierarchy. Along with your standard the 3 flavor oscillation parameters, if they satisfy this, and along with if non-standard parameters also satisfy, you can see if epsilon EE goes to minus epsilon EE minus 2, and epsilon alpha beta stands to minus epsilon alpha beta with star, then this leads to a general mass hierarchy degeneracy in the neutrino sector. So what that to understand this transformation better way, we plot a probability which is called appearance probability P mu to E for DUNE. We studied here for DUNE, and these 4 various band, as I mentioned earlier, normal hierarchy, lower octane, inverted hierarchy, lower octane, depending on your octane and hierarchy, because we have a hierarchy can be normal hierarchy or inverted hierarchy, as well as octane can be lower octane or inverted higher octane. Depending on that, you have a 4 possible choices. So you can see this 4, this pattern here goes to these 4 namings. Now things here to look is that my x-axis is epsilon, which is epsilon EE, which is the NSI parameter. And for simplicity, as I showed earlier, there are lots of NSI parameters, but we are only showing for the epsilon EE. This is because the P mu E appearance channel is mostly affected by epsilon EE. So here you can see this with this magenta line. What I am trying to show is that if you consider this epsilon E 0 here, then you can see for this blue band there is another point here in the yellow band which has same probability. So this magenta curve showing here for this point at 0, you have another point at -2. So you can see if you consider here 0, then epsilon equal to -2, right? So this is an generalized degeneracy. So you can see this from this magenta curve. line. Similarly, you can see from the yellow line. If you consider 1, just put here 1, then you can see epsilon is -3. So you can see from this line. So this is an degeneracy in the neutrino oscillation sector because of the presence of NSI. So here we wrote here that epsilon goes to, this is we name depending on your, this W means wrong hierarchy, right octant and right delta CP. So similarly, this is the name. Another crucial point here with that for 0, -2 and 1, -3, if you consider that epsilon EE is -1, so you can see this is a place where all the 4 curves meet. So that means if you consider epsilon E -1, then you can see -1 degeneracy remains at -1 because -1 will give you -1 and this minus give +1 and +1 and -2 again give -1. So you always fall in this. So this is something region of confusion. So it is clear from here, if that epsilon EE value lies around -1, then Dune cannot solve the hierarchy sensitivity. So this is an ambiguity what we have observed here. Similarly, in the chi-square sector, if we go along, again we studied for Dune. So here the cards show that for, you can see these are my 2 values, like I plotted with the epsilon EE. So 0, -1 and 2, 1. So you can see for, if we consider 0 is a true value, then your another solution is at -2. If you consider 1, then another solution is -3. And if you consider -1, then your solution lies at -1. So this is all the degeneracy that we explained earlier, we are showing at the chi-square level. Similarly, if we also include other NSI parameters, so in this one, I only showed epsilon EE. On the other hand, if you include epsilon eta also, you can see situation is not improving. More parameters means this waving nature is showing you more degenerate solutions. So there is an ambiguity that Dune, if nature supports NSI, then it will be difficult for Dune to resolve the hierarchy sensitive degeneracy. So this is goes under this kind of transformation. And now we like to ask the question: can we resolve the degeneracy? This is a question. And another question is, as I mentioned earlier, the NSI matrix has too many free parameters. Another question one can simultaneously ask is that how to reduce this number of NSI parameters? And to address this, yes, there are way is that as I showed earlier, that if your NSI epsilon EE in my earlier plot, if you see that I want take model independent bounds which lies from -4 to +4, and if now question comes, if you constrain NSI parameter around say very nearby 0, say 0.5 or something, if you can constrain with some experiment or some other ideas, then it is possible that you can measure the hierarchy sensitivity and one can elevate that degeneracy. So there are 2 ways I am going to discuss. One is constrain NSI parameter space, and second is you consider a model-based study and analyze. On the other hand, model-based study has also another importance is that it reduces your number of free parameters. So you can construct a model which can give you 1 or 2 NSI. A model, it is difficult for a model to give you all those NSI non-zero. So this is also an advantage for a model-based studies. Now, question comes, if your model, model prediction is in future, your experiment supports, then you accept that model or you ruled out the model. So now, before I go to model, I'd like to tell you here that what Dune itself may measure the sensitivity of these various NSI parameters. So this is an figure taken from this paper. So you can see that Dune alone measures the sensitivity of those. So these 3 lines are at 68%, 90%, and 95% confidence level. So you can see even at 68%, the parameter space of epsilon here is not so good. It is still allowed value is, you can see from various cards, the red one is around 1 or more than 1 is still allowed. So -1 to +1 is still allowed. So these are the various parameters here I am showing. That sensitivity potential of dunes at what confidence level they can measure this epsilon NSI parameter. On the other hand, if we consider the global fit values, so in the NSI sector also we have global fit data, and which I took from this paper, and you can see I did not mention what is LMA or what is LMAD, but for time being, for my purpose, you can forget this row. You can see this column, these numbers, and you can see this column. So if I tell you that this is the exact solutions, and this is your degenerate solution, which is coming because of that degeneracy presence in your measurements. So you can see for these numbers and these numbers are very different. So if from the oscillation data, you can see till degeneracy exit in the neutrino sector if there is an NSI. On the other hand, with the oscillation measurements, if you include coherent, which in a scattering experiments, and you have heard a lot about coherent in the previous talk, as well as Luis will be talking more about this coherent. So I am not going to give you details of coherent, but if you for my purpose, you can see if you combine oscillation with coherent, then from these two columns, you can see this column numbers are all same as almost this column. So with the coherent, if you add coherent with the oscillation data, then you can elevate these measurements, this degeneracy. So this will be helpful in the near future to rule out the degeneracy due to NSI.
3 minutes.
Yes. Hello.
3 minutes left.
Okay. Yeah. So what I am going to talk here is the NSI from a model. So from the model point of view, as I mentioned, the NSI Lagrangian takes part in this form, where epsilon is depends on your new mediator mass and new coupling. Now you can have two scenarios. If you want epsilon of the order 1 or 0.1, one can have a light mediator, which Luis will be talking more, and one have a heavy mediator where your mass is quite heavy with a coupling order 1. So I'll be talking of this heavy mediator. In this heavy mediator, what we consider to give a concrete model which can lead to sizable NSI is that we consider new to HDMs, where what we did, we along with an additional right-hand neutrino, we have added a extra doublet, and our phi to ER new are odd under global E1, and then you can construct this. Then this is the terms. Once you expand this term and integrate out heavy degrees of freedom, then you can get these terms, and which is the form similar as NSI. Now this NSI term has this pink form. Now if you compare these two, you can find that epsilon EE has this form. Since ER has a global odd E1 charge, you can also combine this with the muon lepton doublet and tau lepton doublet. And from these, you get the possible NSI of this. There are 4 more possible NSI. However, when we study various experimental constraints from the mostly coming from LFB and lab, the LFB data constraints your Y1 of the order very small. So if you see that there's wherever Y1 presents, these terms not going to impact you because it is very small. On the other hand, lab constraint shows you, we plot Y2 versus B2, then this is the only small allowed dark red region is allowed. So this allowed your V2 greater than 2.5 and Y is around this 0.05 or so. So you can see the epsilon E, as I showed earlier, is allowed, and from here epsilon E tau, because epsilon E tau is the term where you can see Y1 is not present. So only these 2 terms are present in our model. So this model helps us to reduce number of free matters in a nice way. So we have 2 parameters, and then we studied that in our 2 Higgs model what this Higgs mass possible extra Higgs mass as well as for Webb and possible NSI, and we show that in this allowed region of NSI, if you consider then you can have more than almost 5 sigma sensitivity, leaving some region here for almost all values of delta C. So this is an outcome of our model. Similarly, recently we are trying to look the same model to study for the ice cube, what you can say for the ice cube. So for the ice cube, only resonance that ice cube sensitivity in the standard model is Grasso resonance, where this kind of this collision take place, where at 6.3 PeV, but ice cube did not observe that. What we try to show that with this 2 Higgs doublet model, can you enhance this resonance? If so, then can you observe that? So for that, we plotted this cross section coming from this our new HDM, and you can see there is an enhancement in the cross sections. We consider 2 cases here. And we expect this is a ice cube events plot. We expect in near future at the higher energy, if ice cube see a few more number of events, then this may tell you that this could be a possible things which can come from this kind of model if it shows, or it can rule out this model.
1 minute.
Okay, so yeah. So lastly, I will talk. I will take 1 or 2 minutes, and the last scenarios where we are trying to combine NSI with mutual reflection symmetry. So mutual reflection symmetry is the symmetry which give you neutrino mass matrix in a certain form where the elements are related. Now, it has a good outputs because it predicts your theta 2 3 45 and delta minus 90. So this is a good prediction, and for recent time this is a good flavor model which explain your neutrino flavor mixing parameters. Now what we try to do here, this epsilon matrix, you can see here too many free parameters. Earlier we discussed with a model base we try to reduce the number of parameters. Here we are trying to address this. If we add a flavor symmetry, can you reduce this number of free parameters? To serve our purpose, we consider here S4 cross Z4 flavor groups with this kind of charge assignments. And what we end up with that is the thing is that your mu, you remember in the Hamiltonian, it is mu dagger that enters. So we construct mu dagger. This is the mu dagger matrix which satisfy your mutual reflexive symmetry. And this the model also gives you NSI terms of this form, which also respect your mutual reflexive symmetry. So you can see now once your NSI matrix satisfy mutual reflexive symmetry, how many parameters you left with? 1, 2, and 3. Out of them, 1 is real and 2 are complex. So you can able to reduce significantly the number of parameters if you study NSI in presence of this kind of symmetry. So that we have shown here recently. So at the end, let me conclude with few remarks. So my idea in these last 20 minutes to tell about the non-standard neutrino interactions. Mostly I try to talk about how it is going to impact on neutrino mass hierarchy, considering a more model dependent as well as independent way. For the model dependent purpose, I consider neutronophilic 2 doublet model and its implication for Dune as well as ice cube. And lastly, I talk about mutual reflexive symmetry's importance to reduce number of NSI parameters and its importance. Thank you.
Thank you very much to Newton. There's time for questions. Yes, Eduardo, please.
Hi, Newton, imagine you have the epsilon EE parameter to be -1. Is there any possibility to use hyper K data with J-Quark?
Any data, if your true value is -1, you will always end up with -1. So it is practically impossible. Now, you can always ask, because when we go from standard model to beyond standard model, if your standard model has, if you have epsilon EE, it is 0. Now, if you have non-standard interaction, then epsilon EE from 0, it can go for 0.5 or something, right?
No, but you show that with Dune, there is a degeneracy, and you cannot say anything.
For time being, we show for Dune, but it is for any experiment.
Hyper K, what happens?
No, any experiment you take, if your two parameters support -1, then you cannot resolve.
Okay.
Okay. Remember, two parameters has to be -1. If your two parameter you take something else, then you can resolve. You understand? Mm-hmm. Two parameter has to be -1. This is the only thing.
Okay.
All right. One more question. You have in the
yes.
Do we have more questions? Yes, Omar. Would you like to ask?
Yeah, just to comment on Eduardo's question, that actually this degeneracy, as Newton said, is valid for oscillations. So that's the reason why you need to go to short distance experiments like this coherent to break this kind of degeneracies.
Okay, thanks. But it will be both coherent, right? Reactor and accelerators are sensitive.
Yeah. Actually, somehow the important point here is that that there is no oscillation in neither reactor nor SMF experiments. It could be coherent or it could be any other cross section that you are measuring without measuring the oscillation effect. So, yes. But of course, coherent is very, very useful for this.
All right. You have more comments? Would you like to respond to Newton?
No, I agree with Omar what he's saying. Yeah, that's why I mentioned that with oscillation you have to go to beyond oscillations, like some kind of scattering experiments and so.
Okay. If there are no more questions or comments, let's thanks to Newton.
And thank you.
Thank you, Newton. And we had to talk by Luis Flores. Luis, can you share your screen? Are you there?
Yes, of course.
Yeah. So
can you hear me?
Yeah, we can hear you. So your talk is on new interactions in coherent elastic neutrino nucleus scattering measurement. So whenever you please share your screen, we can see it.
There, can you see it?
Yeah, perfectly fine.
Okay, thank you. So, hi everyone, my name is Luis Flores. Thank you. I want to thank the organizers for the opportunity to present in this meeting. So this is the name of my talk, New Interactions in Coherent Elastic Neutrino Nucleus Scattering Measurements. This is a work in collaboration with Eduardo Peinado and Newton Nath. So this is the outline of the talk. First, I'm going to introduce what this process called coherent elastic neutrino nucleus scattering. We can refer to this as SEVENS process. Then I'm going to introduce these non-standard neutrino interactions, just a small part of this. Then I'm going to discuss a model that we produce. It's a U1 prime model that can produce these non-standard interactions. And then I'm going to give some final remarks. So the first part of the talk, I'm going to go a little faster since Stella already covered all of this, the introduction part. Okay, so what is SEVENS? This process occurs when a neutrino is scattered by a nucleus in a detector via a C boson mediator, meaning this is a pure neutral current process. This scattering process was first predicted by Friedman almost more than 40 years ago. And the main feature of this process is that the energy of the neutrinos has to be smaller than 50 MeVs. So if you met this condition, it means that your transfer momentum is going to be very small compared to the size of the nuclei, which is the condition shown here, right here. Okay, so this is the Feynman diagram for this process. As I was saying, the neutrino is scattered by a nucleus, but the neutrino sees this nucleus as a whole element, not the components. Therefore, we can write the cross section for this process in this way. As you can see, it depends on the mass of the nucleus, on the recoil energy of the neutrino, of the nucleus, sorry, and the incoming energy of the neutrino. Here we have defined this QW, which is called the weak charge. As you can see, it depends on the number of protons of the nucleus, which is this C. It depends also on the number of neutrons, and it depends on the nuclear form factors for each protons and neutrons. It turns out that the first term is smaller, it's very small compared to the second one. So one can see that this cross-section scales as n squared. So this is a good feature of this process because one can use heavy nuclei in order to get more events. As you can see in this plot, the cross-section scales as n squared. So it is useful to you to have heavy nuclei. On the other hand, this cross-section is bigger than the other neutrino processes. In this plot, you can see all the blue lines are the SEVENS cross-section for the different nuclei, and it is quite bigger than other processes such as neutrino electron scattering. So this is an advantage that some experimentalists are using right now to have more events. So why do we consider important these seven processes? Well, there are a lot of physics you can do with these kind of processes. You can have low energy measurements. You can say something about nuclear physics. And of course, you can have searches for new physics signals. And now I'm going to discuss a little bit about these 3 points. For the low energy measurements, there are already measurements of the weak mixing angle. As you can see in the plot here in the left, you can extract this parameter from neutrino electron scattering, either from reactor or accelerator experiments. But as you can see, the error bars are quite large. And you can also extract this weak mixing angle using Sevens measurements. And one can expect that the error bars are smaller for these kind of experiments. On the other hand, you can also say something about nuclear physics. Since the cross-section depends on the nuclear form factors, as you can see here, the nuclear form factor provides information about the neutron RMS radius. So you can, if you have data from these seven processes, you can actually do a fit to get a value for this neutron RMS radius. And for searches for new physics, just to name a few, Stella already covered this, but you can have searches for sterile neutrinos. As you can see here, you can put limits on the mass difference and the mixing angle. You can also say something about non-standard neutrino interactions. You can put limits to these parameters. You can also look for neutrino magnetic moment signals. As you can see here, this is the black line is the recoil spectrum for the seventh process predicted by the standard model. And if you consider a non-zero neutrino magnetic moment, this line gets higher at low energy, at low recoils, nuclear recoils. So if you have a detector that is sensitive enough to reach these recoils, you can actually look for these kind of signals. So as Estela mentioned before, this is a process that was believed to be very hard to measure, since you need very sensitive detectors and a neutrino source with a lot of events. But luckily for us, the coherent collaboration has measured this process twice, actually. First, 3 years ago, they used a cesium iodide detector. And more recently, this year, they also use a liquid argon detector called SENS-10 detector to measure this process with great accuracy. So the coherent collaboration used accelerator neutrinos at the spallation neutron source, but there's a handful of experiments that are looking to measure the signal using reactor neutrinos. Here I show only a few of them, but there are some of them are already taking data, some of them are not, but we are hoping to get that they get a signal for these events. So now moving to the non-standard neutrino interactions, Newton already discussed this in his talk. So very briefly, as you can see, if you consider interactions beyond the standard model, you can actually write an effective Lagrangian involving these interactions with neutrinos, with other fermions. And you can parameterize the strength of these interactions via these epsilon parameters. So if the neutrino has these non-standard interactions, they should affect the seventh cross-section. So as you can see here, these NSI parameters enters the cross-section through the weak charge, this Q here. So this is the way that the NSI enters the cross section. Okay, what we did in this work with Newton and Eduardo was to propose a model with an extended U1 prime symmetry that can produce these NSI parameters. So the ingredients of our model is, of course, the new symmetry, the new U1 symmetry. Here we considered a variation of the B minus L symmetry, which is right here, B minus 2 L alpha minus L beta. We also considered 3 right-handed neutrinos and 2 symmetry breaking scalar fields. We considered 2 because it has been proven that having 2 symmetry breaking scalar fields is consistent with the latest oscillation data. So the charge assignments for our new symmetry are shown in this table here with X for the leptons and the right-handed neutrinos. And this X can take the values either 0, -1, or -2. And we consider these values because they give an anomaly-free model, which is something we need. So if we consider these three charges in various ways, we can have 6 possible scenarios. And in these possible scenarios, we can construct the neutrino mass matrix considering a type 1 seesaw, as you can see here. So this gives us 6 possibilities. In each one of these possibilities, you can see there appears only 2 NSI parameters in each of them, different for each type of neutrino mass matrix. As you can see, they have names already, A1, A2, B3, B4, and the last one don't have a name. And the reason is why the first 4 possibilities are in good agreement with the latest oscillation data. The bottom 2 are forbidden. And actually the first 2, A1 and A2, are in better agreement than B3 and B4. So we're going to show some phenomenology we can extract from these 4 scenarios that are allowed. One of these phenomenology consequences is the in neutrinoless double beta decay. This term only appears in the B3 and B4 scenarios. In the A scenarios, this effective Majorana mass is actually 0. So for these scenarios, we can have a prediction here shown in blue, this blue line, which is B4 is still allowed by the Kamlan's N400 data, and B3 is a little more constrained. This is one of the predictions of the model. Also, we can have a prediction on some oscillation parameters, like the delta CP phase and the 2 Majorana phases. So here I show, for example, for the A1 and A2 scenarios, we can fix different values of the mixing angle theta 2-3. The best fit scenario, the maximum value, and the latest T2K result. And this, by fixing this angle, we can have some predictions on the masses of the neutrinos, on the sum of the masses, and also a prediction for the CP violating phase, which is in agreement with the latest T2K results.
3 minutes left.
Okay, thank you. Okay, what else can we extract from this model? So as you know, having this extra symmetry, this extra symmetry is associated with a new gauge boson, which it's often called a Z prime boson. And this Z prime has, there are some parameters associated with it, such as its coupling, this G prime, and its mass, MC prime. So if we consider an effective interaction between neutrinos and quarks, mediated by this Z prime boson, we can write an effective Lagrangian in this way. And if we compare this Lagrangian with the NSI Lagrangian I discussed before, we can set a relation between the NSI parameters and the parameters of the Z prime in this way. As you can see, here the charges of the new symmetry appear too. So these epsilons depend on the coupling, the charges, and the mass of the Z boson. So what we can do to extract some information from Seven's experiment is plug this in the cross-section that I showed before and do a chi-square analysis using measurements from Seven's experiments. So these are our results. This is for the type A1 and A2 mass matrices. As you can see here, this blue region is the exclusion region for this parameter space. This is the exclusion region set by the first coherent data. And the orange line is the limit set by the second measurement using liquid arc. So we show here also limits coming from LHCb. And as you can see, LHCb is better to constrain this parameter space at higher masses of the Z boson. And we also have constraints set by oscillation experiments, this purple line here. So something we did in this work was to go beyond the current measurements of Sevens and simulate future measurements of coherence using different detectors that are upgrade plans from the coherent collaborations. Some of them are a germanium detector, a sodium detector, and a larger liquid argon detector. I believe it is a 1 ton detector. So as you can see here, the limits set by these new detectors are better than the current ones. And there's a few reasons for this, but the most important one is the mass of these detectors and the thresholds they can achieve. So this is for these are the results for the A1 and A2 scenarios where there is no electron NSI parameter. But as you can see here, for the B3 and B4 scenarios, there is an NSI component coming from electrons. So here we have more constraints on this parameter space, and these constraints are coming from beam dump experiments shown here in yellow. So these are more constraining than any other experiments, but only at lower masses of the Z boson. Besides all of this, we also wanted to investigate how the reactor experiments could handle this kind of constraints. And since in reactor experiments you only produce electron antineutrinos, that is why only in these two scenarios you can have constraints from these experiments. And here we are showing that, for example, we show that the Conus reactor experiment will this magenta line will set up the better constraints for this parameter space. But still, as you can see in the right panel, LHCb has a bigger exclusion region for higher masses, even better than the expected Conus results. So to finish, I'm going to give some final remarks. First, about Sevens, the process itself. It is a very powerful tool to study low energy parameters such as the weak mixing angle. It provides a great possibility to find signals for new physics, different ones. Also, the future coherent upgrades and some reactor experiments can improve all these searches for new physics. And as for the model, we have shown that it is consistent with current oscillation data, at least 4 of the possibilities we found. And these possibilities are very easy to study since you only change the charges, the new charges. And also it provides predictions for neutrino-less double beta decay and for some oscillation parameters. And that's it. Thank you.
Thank you, Luis. Let's take a couple of minutes for questions or discussions. So are there any questions, Salvador, in the chat or?
No, I don't see any questions up to now.
Okay, if no one have questions for the moment, let's please, since we're a bit late, let's please thanks to Luis, and thank you, Luis, and we're going to the next talk by Oscar Sanders. Are you around, Oscar?
Yes, I'm here.
Can you please share now your slides?
Yes,
Oscar,
of course.
talk about current and future constraints on stellar neutrinos from sevens. So please.
Okay, thanks. Okay, good day, everyone. My name is Oscar Sanders. I'm from the physics department at Simvestab, and I'm going to talk about current and future constraints on stellar neutrinos from sevens. I would like to mention that this presentation is based on the following papers, just in case you want to check it out. And the outline of my talk is the following. First, I'm going to give an introduction in which I will talk about neutrino oscillations, stellar neutrinos, and sevens. Then I'm going to give some future perspectives on experiments that can measure this process and how we can use them to study stellar neutrinos, such as the coherent collaboration, the European spallation source, and the Kapchan-Mills experiment. And finally, I'm gonna talk about some other studies that can be done using sevens, such as weak mixing angle and non-unitarity neutrino mixing. And finally, the summary of this talk. So first, let's talk a little bit about neutrinos. As we know, the existence of neutrinos were proposed in 1930 by Pauli, studying the electron energy spectrum in the beta decay. Since then, the neutrinos from the electron, muon, and tau were discovered on 1962, 1965, and 1975, respectively. In the standard model, the neutrinos are described as massless and chargeless particles that comes in these 3 different flavors, but recent experiments suggested that neutrinos may have multiple mass eigenstates, indicating a mixing between them. The neutrino oscillations were first proposed by Bruno Pontecorvo on 1957 as an analogy to Kaon's oscillations, and later in 1998, the Super Kamiokande detector observed an anomaly in the atmospheric neutrino flux that can be seen in this plot. In blue, we have the expected number of events without neutrino oscillations, and in red, we have the expected number of events, but considering neutrino oscillations. And as we can see, the experimental data is in good accordance with the case of neutrino oscillations, so this was the first evidence of this process. Now, neutrino oscillations in vacuum are a quantum mechanical phenomenon that is possible by the existence of non-degenerate neutrino masses and lepton flavor mixing. The flavor eigenstates are related to the mass eigenstates by an unitary transformation given by this matrix over here. But in shorthand notation, the relation reduces to this one, in which there is a relation between the flavor eigenstates and the mass eigenstates at 0 time. This will be useful in the determination of the neutrino oscillation probability. This matrix can be parameterized in different ways, but one of them is using 3 mixing angles and 1 Dirac phase that accounts for CP violation. In this case, this matrix P represents the Majorana phases, but as we will see, they do not contribute on the oscillation neutrino probability. Now, the propagation of the neutrinos causes the mass agency states to evolve with its own phase factor given by this term, and this modifies the superposition. If we then come back from the mass agency states to the flavor agency states, we have this relation that can be used to find the probability amplitude of the oscillations to a different flavor that is given by this equation over here. Finally, if we consider the neutrinos to be ultra-relativistic particles, we can find the general relation for the oscillation probability from a flavor alpha to a flavor beta given by this equation over here. I think it is important to mention that the probability for the case of antineutrinos is the same as this, but with the difference of a minus sign in the last term. This relation is found for the case of 3 flavor neutrinos, but it is a good approximation for many experimental situations to work only with 2 neutrino flavors. In this case, the oscillation probability reduces to this one, and it is important to note that this case of oscillation probability is the same for neutrinos and for antineutrinos, and also the problem reduces only to 1 mixing angle and 1 difference of square masses represented by these parameters. It is important to remember this because if we work with the units of the term inside the sign, we get to this final relation, which is the one used for the following calculations. As we mentioned, neutrino oscillations can describe solar and atmospheric neutrino fluxes, but there are some anomalies that cannot be described by a 3-active neutrino model. As we can see in this plot, we have in this axis the reactor to detector distance, and in this axis we have the ratio of observed to predicted events. As we can see for the case of atmospheric and solar oscillations, we have a good agreement with the case of a 3-neutrino model that is represented with this dashed line. But for the case of reactors, there is a difference on the expected value with respect to the actual data. There are some extra anomalies, such as LSND and mini-boon excess of electrons, neutrino, and neutrinos, and the gallium anomaly, in which it is observed a deficit of electron and neutrinos from calibration sources. If we consider these anomalies and interpret them as a consequence of neutrino oscillations, then we can find the following values for the oscillations parameters, let's say the mixing angle and the delta m square. For the case of the mixing angle in this form, it must be a value between 0.1 and 0.2. And for the case of the delta m square, a value between 1 and 2 electron volts squared. But since the number of active neutrinos is established by the invisible decay of the zeta boson given by this relation, it is necessary to include in this scenario the existence of neutrinos that do not interact via weak interaction. These neutrinos are the so-called sterile neutrinos. There are different experiments that have put tension on the existence of sterile neutrinos, but there are also some experiments, such as the case of neutrino 4, that observe the effect of oscillations, reporting at a confidence level of 2.8 sigmas, the following values for the mixing angle and for the delta mass square that we can see in this plot and in this plot. So Stevens can give us another channel to study neutrino oscillations in order to confirm or neglect the existence of sterile neutrinos. So let's talk again about coherent elastic neutrino nucleus scattering. In this process, the neutrino scatters from the nucleus via a neutral charge interaction, and we say that this process is coherent because the neutrino interacts with the nucleus as a whole rather than with the individual nucleons or group of nucleons, increasing dramatically the cross-section, as can be seen in this little plot right here. In blue, we have the cross-section for the case of Stevens, and the other lines represent other couplings of neutrinos. We can see there is a difference of about 2 orders of magnitude for most of the cases with respect to Stevens. And finally, we say that this process is elastic because the neutrino and the nucleus are the same at the initial and final states, thus conserving the total kinetic energy. The problem with this process is that the great difference between the masses of the neutrino and the nucleus causes the nuclear recoil energy to be quite small from around 100 of electron volts to few kilo electron volts, making this process very hard to measure. Since the prediction of events, many years have to pass until the coherent collaboration measured this process for the first time, using first a CSI detector and recently a liquid argon detector. Now, for the statistical analysis to find the sensitivity for the different parameters of oscillation, we use a chi-square analysis given by the following function, in which we compare the experimental number of events with the theoretical number of events that may depend on different parameters represented by this letter X, and the background number of events. Each one of these number of events with its corresponding nuisance parameter that corresponds to the different uncertainties of the detectors. And sigma represents the statistical uncertainty given by the square root of the total number of events, and the theoretical number of events is calculated by the following relation. We mentioned that coherent was the first experiment to detect events, but there are different experiments that are planning to measure events, such as future detectors for the same coherent collaboration, the European Spallation Source, and the Kapchan-Mills experiment at Los Alamos National Laboratory. For the experiments that are still under construction, it is possible to propose an ideal baseline to study sterile neutrino oscillations. In this plot, in these two plots, we have the chi-square analysis as a function of the baseline for the different experiments. In this case, we are analyzing SENS 10 from the coherent collaboration, the Kapchan-Mills, and the European Spallation Source for two cases, one with 10 kilograms of mass detector and the other one with 1 ton. As we can see, for all of these experiments, the ideal distance to study sterile neutrino oscillations is around 30 meters. If we take this into account, we can find the limits on the possible values for the mixing parameters. As we mentioned, we only need two of them in the case of two flavor oscillations, the mixing angle and the delta M square. We do the same for the experiment that we just mentioned, since 10 from the coherent collaboration, CCM, and the European Spallation Source. And we consider three different distances around 30 meters that we found to be the ideal baseline. And for the left panel, we have the considering only oscillations from electron neutrinos to sterile neutrinos. And in the right panel, we consider only oscillations from mu neutrinos to sterile neutrinos. We do the same for the other experiment that we mentioned, the European Spallation Source, but considering a hypothetical case of 1 ton. And we can see that this can give us the better sensitivity to the study of these parameters due to the big mass that can give us a lot of data to study. Now, as we mentioned, the coherent collaboration have a lot of detectors that are under construction in order to study this process. This is the case of these other three detectors that are a detector of germanium, the detector of liquid argon, with which they already obtained the results, and a detector of sodium iodide. We do the same analysis as the previous plots. We try to find the sensitivity to the mixing parameters, the mixing angle, and the delta M square. But in this case, we analyze different efficiencies and different uncertainties for each one of the nuisance parameters that we mentioned earlier. This is the case again for oscillations between electron neutrinos. And in this case, we show again the sensitivity, but for the case of oscillations between mu neutrinos and sterile neutrinos. As we can see, there is a difference in the sensitivity between the electron case and the muon case, because since the fluxes of the neutrinos are produced by spallation sources, the number of mu neutrinos is bigger than the case of electron neutrinos.
5 minutes left.
Okay, thank you. Now, another studies that we can do using Siemens is the case of the weak mixing angle. As we know, weak mixing angle is a fundamental parameter of the standard model, and any deviation from its predicted value may be due to new physics. So in the first plot, we show the actual values obtained using the data from the CSI and the liquid argon detector. As we can see, there is a good improvement between the first and the second detection of Stevens, and with the last case obtaining the following value of the weak mixing angle. And again, we can study what may be the sensitivity to this parameter if we can improve the efficiency and the uncertainties on the three future detectors of germanium, argon, and sodium iodide for the coherent collaboration. Finally, another physics beyond the standard model that we can study using Siemens is the case of the non-unitarity of the neutrino mixing. And we study this by the introduction of neutral heavy leptons, which arise naturally in some extensions of the standard model and have a possible role as messengers of neutrino masses. The presence of extra heavy fermions imply the non-unitarity of the 3x3 light neutrino mixing matrix. As you remember earlier, we said that neutrino oscillations was between the unitary transformation from the flavor to the mass eigenstates, but in the presence of these extra heavy fermions, this matrix is no longer unitarity, and this produces an oscillation probability at zero distance given by this equation, by these relations that depends on these parameters alpha. And these parameters alpha are ruled by these triangular inequalities. If we take into account the triangular inequalities and we include this oscillation probability into the initial flux, it is possible to obtain limits on the values on these parameters as can be shown in this image. This yellow region represents the unphysical values given by these triangular inequalities, and each color represents the limits that can be achieved using each one of the detectors. As a summary of this talk, Siemens has a great potential in the study of physics beyond the standard model, as we talked with stereo neutrinos and the non-unitarity of the neutrino mixing matrix. There are different future experiments aiming to measure this interaction, and there is a lot of work to do in this future perspective by considering more realistic characteristics such as quenching factors, the real distances, the real masses, and of course, the uncertainties that can achieve each one of the detectors. And thank you very much for your attention.
Thank you very much, Oscar. It's a very clear talk. So there's time for questions or comments from the audience. Do we have any questions, Salvador?
No, I don't see questions from YouTube. Let me check.
The chat or in the...
No, no questions in the chat or YouTube. Maybe just wait 1 minute.
I have a question.
Yeah.
Yeah, concerning the violation of unitarity. What are the scale of the fermions, heavy fermions you are assuming to in order to get something?
Sorry?
What would be the scale of these heavy fermions in order to have enough violation of the unitarity? I mean, because if those are quite heavy, the violation is smaller, right?
Well, yes. Well, the simple presence of these extra heavy fermions affects the value of the mixing matrix, introducing a new matrix that arises from these heavy neutral fermions that is given by these parameters over here. So these parameters are the ones that can give us how much is violated this unitarity.
Yeah, but what I meant is naively one expect that this violation is related to the neutrino masses and the heavy fermions. It's
Yes.
like the ratio. So with those lines, I guess that you should assume something on that scale.
Okay, I don't remember very much right now, but if you let me check it, I can answer you in the chat.
Thank you.
Right. Are there more questions or comments? Oh, I received questions from Estela. Estela, can you put your question? Can you ask yourself? Just let me repeat the questions. She put this in the private chat. The non-unitarity parametrization has an NSI equivalence. Is new physics parametrization more convenient in either case?
Okay, can I see the question, or can you repeat it, please, one more time?
Yeah, I'm going to copy in the chat and repeat it. The non-unitarity parametrization has an NSI equivalence. That's a question, the first question.
I'm not sure about it.
And the second is new physics parametrization more convenient in either case?
Maybe I can comment?
Sure.
In principle, you have some relation, but this parametrization is more focused on only on the case of non-unitarity. So what we have found is that actually this parametrization is very useful when you are using oscillations, and it is very clear for somehow, and that's the reason why we don't use NSI in this case, because when you try oscillations and you consider this case, this is a kind of transparent notation.
Okay, thank you.
Thanks.
Thank you. All right, any other question or comment? If not, I think it's time to stop this session now. We will have our poster session from now to 5:45 p.m. So that's it. That is the next hour and a half. When the authors of the poster will be replying in this link that I will again put in the chat, so you can click at the posters and see the videos and comment in the video, and authors will have to reply. You can ask your questions. Please participate. There will be a jury. So I think, Salvador, do you want to say more about this?
Yes. Thank you, Ivan. I want to tell everybody that please consider that this is a new system we are trying. So please let us know how you see it, and please just participate.
So thank you very much to everyone. So hopefully you will be able to look at the posters, and we'll see you tomorrow at 9 o'clock. Thank you, everyone.